Here I have two examples of the initial disturbance. On the left we have carrot respiration measurements and they all start from high values. On the right we have some barley grain germination measurements. They all start from low values, negative values. And the reason why these 8 measurements all come from above is that the samples were warmer than the calorimeter when they were charged. And here they all come from below because these vials were lower temperature than the calorimeters when they were charged. So these initial disturbances, they are artifacts dependent on the temperature of the vial when it was charged. Let's look at this in some detail. Here is a calorimeter or a vial, and here comes the calorimeter, the heat flow sensor and the heat sink. This is all very schematic. Let's say that the heat sink and the calorimeter is running at 20 Celsius. And we have a sample here, which is a small insect. And then the result can look like this, where we have a soldier beetle larva in this case, and the resting metabolism generates a thermal power of approximately 150 microwatts. So 150 microwatts. Now the signal from the calorimeter is generated by a temperature difference. So the metabolism of the insect actually heats up the insect and this part slightly, gives a temperature difference, and that gives a signal. Now the question is, how much warmer is the insect and the vial compared to the calorimeter? Well, in this case, the temperature, or the over temperature, is approximately thousands of a K. It's not much. It's very, very small. Very, very small temperature difference. Now let's look at the case when we have initial disturbance instead. So I will draw the same calorimeter. Like that. And let's say we have the same insect also in the calorimeter. Now we have just charged the vial, and the vial came from a room which was, let's say, 5 degrees warmer than the calorimeter. So this means that we have an over temperature here of 5 K, and that's just when we have charged the vial. Now, just looking at these numbers here, there is a proportionality between the temperature difference and the thermal power. 5K corresponds to approximately 1 watt. And this is a huge thermal power, far higher than can be measured by normal isothermal calorimeters. This thermal power means that the calorimeter goes far out of range. And this is initial disturbance, and this very high thermal powers and very high signals that we get, they are not at all caused by the insect. They are caused by the wrong temperature of the vial. So when we make a measurement, we have time and we have thermal power, and let's say we have these 150 microwatts, the insect thermal power. Now if the vial that we put into the calorimeter is warmer than the calorimeter, we will generate apparent very high thermal powers, which means that we actually go out of range for some time. And then we go in range and we can start measuring still high values, and then this will decrease, and the decrease will be exponentially, and it will end up at the thermal power of the insect after some time. So this is what happens when the temperature in the room is higher than the temperature in the calorimeter. And if it's lower temperature in the room, we end up at typically out of range values, but on the negative side, and then get an exponential decay back once more to the thermal power of the insect, the true thermal power. So it does take some time. It does take some time to come to the time when we are measuring the true thermal power of our sample. And this time here is typically 20 to 60 minutes. And before this, we have these exponential decays plus the thermal power of the sample. But these exponential decays, remember, they are just artifacts. They are apparent thermal powers. They are not true thermal powers from the sample. Now, when can this be a problem? Well, I'll show two cases. The first one corresponds to chemical reaction, hydrolysis, alkaline hydrolysis of a polymer, polylactic acid in this case. And here are 8 measurements, and this reaction is sort of first order, quasi-first order. So this is an exponential decay. This is from the reaction, from the chemical reaction. This is ours here. But in this case, we wanted to integrate these curves. The thermal power, if it's integrated, it gives the heat. And the heat, now joules per gram polymer, means we can calculate the enthalpy of the process. So we integrate and we see that all these curves ends up around 800 joules per gram. That's good. But the problem here is that we don't know the thermal power during the first half hour or hour because of the initial disturbance. So in this case, to construct this diagram, to integrate, I removed the first hour of these measurements, replaced it with an extrapolated curve based on the measurements after 1 hour and later, an exponential curve fit. And then I could construct this heat. It would have been better if I didn't need to do this, but I had to do this because of the initial disturbance. Second example, now this is a cement hydration curve, and this is a very common measurement made with isothermal calorimeters. And here you see the main peak of hydration, 10, 20, 30 hours. And this is very typical of cement hydration. And if we're interested in this main hydration, the initial disturbance is not a problem, because the initial disturbance comes during the first hour and the main reaction doesn't start until after 2 or 3 hours. However, if we are interested in the initial reactions, because here there are initial reactions. When the water contacts the cement, reactions will start. And we may want to study those reactions, but that's difficult if we, like in this case, mix our cement paste outside the calorimeter, put it into the calorimeter, and then start the measurement with a huge initial disturbance. So then we need to do something else, and I will talk about that and about other things in the second video on initial disturbances.